Here are the problems on relativity, and when you work out these problems, do remember that the concept itself is a little bit complicated when compared to the other topics in physics. So you'll have to be that much more careful in trying to understand what is being done. The first question talks about if you were to travel to a star 125 light years from Earth at a speed of 2.5 times 10 to the 8 meter per second, what would you measure this distance to be? Now here what we need to use is the idea of length contraction, where L is equal to L naught by gamma, where L naught is the length in a frame of reference in which there is no velocity, no movement, and L is the length from the perspective of a moving frame of reference. And gamma is the constant, which is given by 1 divided by 1 minus v squared by c squared. Okay, it's actually 1 divided by square root 1 minus v squared by c squared. And when you see that the velocity here is 2.5 times 10 to the 8. C is always the velocity of light, so when you put that, okay, now I have added the 1 divided by, so you get 1 by 0.5527, which comes out to be 1.80. And therefore, the length would appear to be 125 light years. You always keep it in light years, divided by 1.8. That is 69 light years. So the distance would be measured to be 69 light years. In this second question, suppose you decide to travel to a star 65 light years away at a speed that tells you that the distance is only 25 light years. How many years would it take you to make the trip? Now this is just like the previous question, except that in this case the L naught and the L both are given, and we got to figure out how much time or how many years it would take to make the trip. So using the same formula as before, and knowing that gamma is 1 divided by square root 1 minus v squared by c squared, we can first find gamma from L naught and L. You get it as 2.6, and then once you get gamma there, we can try to find velocity from this equation. What I've done here is square both sides and rearrange, and then I'm trying to find the velocity in terms of the speed of light. So 1 by gamma is 2.6. So when you do the calculations here, that's what you get. Now taking the square root on both sides, you get it as 0.923 c. And then, knowing that this is the speed at which the movement takes place, time is nothing but distance divided by speed, right? Time is distance divided by speed, and the distance is 25 light years. So now, because it's a distance and it's in light years, you multiply with c, right? And the velocity is also in terms of c, so the c's both would get cancelled, and you know that the answer is 27 years. In this question, the escape velocity from the Earth is 11.2 kilometer per second, which is considerably less than the velocity of light, and so when you're asked to find the percent decrease in the length of a 65.2 meter long spacecraft, the percent decrease is going to be really, really small, because when compared to the speed of light, 11.2 kilometer per second is negligible, right? So let's calculate that, keeping that in mind. Velocity is far less than the velocity of light. And that's the formula for length contraction. And since we're looking for the percent decrease, I've made L by L naught the subject. And now I'll have to change velocity. Okay, the square root is written as raised to half, you know that. And an approximation of this relation using the binomial theorem is you take the power half and multiply it here, v squared by c squared. That's an approximation which can be applied when this term is really small, which is true in this case. Okay, now 11.2 kilometer has been changed into meter. To square that, and you get that as that term as 6.97 times 10 to the negative 10. So you see that this is actually the decrease, because it's 1 minus something, right? That's the decrease. But to get the percent decrease, you got to multiply with 100. So that's 10 to the negative 8, of course, when you multiply this quantity, the decreased quantity, by 100, right? So that's negligible, that's so small. How fast must a pion be moving on an average to travel 25 meters before it decays? The average lifetime at rest is repeated, is 2.6 times 10 to the negative 8 seconds. So the pion is just born and it dies within 2.6 times 10 to the negative 8 seconds, which is a real small lifetime. And during that time, it's moving, and we got to find out how fast it should move to make up 25 meters during that time. Right, so velocity is distance divided by time. And the reason why I've written it this way is because of time dilation. We know that delta t is delta t naught times gamma, right? And so we get this when you rearrange. I've taken this to the other side. It goes to the top, and d goes to the denominator, and then square both sides. Here it will become v squared. This will become squared there, and here the square root will vanish. The idea is to collect the terms having velocity v onto one side, which is what I'm doing now, and then I can take out v squared by c squared as a common factor, then put 1 to get this, and then here I'll have to have c squared. I've just taken v squared by c squared common, and then therefore from there v squared is c squared times 1 divided by this whole thing. You got to take a careful look at this to understand, because it's kind of complicated. And then I've taken the square root on both sides, so v is equal to c and the square root of this whole thing. And Now C is 3 times 10 to the 8. Delta T naught is 2.6 times 10 to the minus 8. And D is 25 meters. So when you substitute all that, you get 0.95 C. So the pion had to be moving at 95% of the speed of light to move 25 meters before it decays. How much work is required to accelerate a proton from rest up to a speed of 0.998 c? And in the B part, what would be the momentum of this proton? How much work is required to accelerate a proton? Okay, work is nothing but the change in kinetic energy, and we have the formula for change in kinetic energy as gamma minus 1 mc squared, and gamma is 1 by 1 minus v squared by c squared. I have not written that down, but you will have a c squared here, and when you divide by c squared, the two c squareds get cancelled. Hope you understand that. And then mc squared is the rest energy of the proton, which is a constant, and you have to know that the rest energy of the proton is 938 mega electron volts or million electron volts. Okay, so 938.3 mega electron volts. And then when you calculate all this, you get 13.9 times 10 to the 9 electron volt. Remember that this is mega, so it will be 10 to the 6. And then when you calculate this number and multiply, this is your final answer. Now to find the momentum, relativistic momentum is not just mass times velocity, it's gamma times mass times velocity. So you see that? Gamma times mass times velocity. And now the wonderful thing is that mass times velocity can be written as 938.3 MeV by c squared. Okay, because if you divide the rest energy by c squared, you get the momentum. All right, I think I should write that, because if you divide kinetic energy, if you divide, now we've used K, so if you divide K by c squared, you're going to get P, momentum. So that's what I've done here. I've divided, we know that's the energy, kinetic energy of a proton at rest, and divided by c squared. Okay. That gives the mass. I must say that gives the rest mass. That gives the rest mass of the proton. Sorry for that. That gives the rest mass. And then when you multiply with the velocity, you get this momentum. So this whole term is the momentum. Okay, let me say that again. This is the rest mass of the proton, and that is its velocity. So this is m times v. Okay. E by c squared gives the mass. I've written that there. When you do all that calculation, you get 14.8 times 10 to the 9. And the unit will be electron volt by c, because one of these c's will get cancelled, but you'll have a c in the denominator. So that's the unit of momentum. What is the momentum of a 950 mega electron volt proton? This is similar to the last problem. So what is given is 950 mega electron volts, which is and we can write the total energy is the kinetic energy plus the rest energy. Because even if it's not moving, the proton has this much energy. That's called the rest energy. Now it's moving, so it'll also have kinetic energy. So if you add the two, you will get the total energy. Okay, that's one formula. And the second formula, which is not connected to this, is PC squared is E squared minus MC squared. So you have these two. MC squared whole squared actually. So now you have this, and now we can substitute for this E. We can substitute for this as K plus MC squared. So you will have K plus MC squared the whole squared, because it's E squared, right? Minus MC squared whole squared. And when you simplify this, you're going to have three terms here. The first term is going to be K squared. Second term will be 2K MC squared. And the third term will be exactly this term, but positive. So what's going to happen is the third term here gets cancelled with this term. So finally we only have two terms, which is K squared plus 2K MC squared. Remember, on the left hand side we have PC whole squared. So when you take the square root, you have PC on the left side, and then the square root of this. And this has been split this way because we know MC squared is the rest energy, and it is 938.3, right? Another thing has been done here. K has been taken out and put 1 here to get this term, plus 2MC squared by K to get this term back, all right? So, and K is the kinetic energy, which is given as 950, and then MC squared is 938.3. So when you do all that, you get 1638 mega electron volts, and the unit should be mega electron volt by C, because PC was that much. Therefore, what's P? P is that divided by C. All right. And then calculate the kinetic energy and momentum of a proton traveling 8.15 times 10 to the 7 meter per second. By what percentages would your calculations have been in error if you had used classical formulas? Once again, it's about calculation of kinetic energy and momentum. Okay, kinetic energy is given by gamma minus 1 MC squared, which is this. So K is gamma minus 1 MC squared. Gamma is 1 by root 1 minus V squared by C squared, minus 1 MC squared. And by now MC squared is the rest energy of the proton, and velocity is given. So plug all those numbers. Okay, 938.3 there, mega electron volts, and you calculate that. Really be careful when you calculate this, because it looks easy when you calculate, and it is easy, but you got to be really careful when you do that number. And then to find the momentum, gamma times mass times velocity. I just substituted the value of gamma there, and then you can write that as 1 by C MC squared V by C. Okay, take a close look at why I had to do that, because I always need MC squared. You see, I need this MC squared because I can write it as 938.3, and then V by C, and then this term root 1 minus V squared by C squared. Again, there is a bunch of calculations there where you have to be careful, and if you do it carefully, you're going to get 265 mega electron volt by C. Now, this is a problem that deals with relativistic addition of velocities, and in order to understand this problem, I have just drawn a diagram here where you have two frames of reference. One of the frames of reference is S, and there is an observer at the origin, O, and this frame of reference is not moving. The second one is the frame of reference S prime, and it is moving with the velocity v compared to S. So the observer at O would feel that another observer at the origin of S prime, let's call him O prime, is moving at a velocity v. So O feels that O prime is moving at the velocity v. Is that clear? But now, in this frame of reference S prime, there is something else moving, and that is moving at the velocity ux prime according to O prime. Now the question is, what will O think about the velocity of this? That would be called ux. So now you see there are three velocities. One is the velocity with which the frame itself is moving compared to this, that's v. The second is the velocity ux prime with which something is moving compared to O prime. And the third is ux, which is the velocity of that same event according to the observer O. Okay, and the same setup is there in this problem. You can see there are two rockets, rocket A and rocket B, and then there is the Earth. So we'll have to now figure out which are the two frames of reference and which is the actual event. Now the addition of velocities is given by this formula. Ux is equal to, so ux is always going to be the thing that we're going to find out, and therefore you have to assume that rocket A is the S frame and the Earth is the S prime frame, which means rocket B is actually the event moving with a velocity ux prime. Okay, so the velocity of the Earth now relative to the rocket A, how much is that? What's the velocity of the Earth relative to rocket A? A person in rocket A, wouldn't he think that the Earth is moving backwards at 0.65 c? Yes. Therefore, the velocity of the Earth relative to rocket A is negative 0.65 c. Negative 0.65 c. So, now the velocity of rocket B relative to the Earth. Velocity of rocket B relative to the Earth, how much would that be? That is what we call ux prime, and that is given as 0.85 c. So now it's clear. We have to find the velocity of rocket B with respect to A, which is ux, and the formula ux is ux prime plus v divided by 1 plus vux prime by c squared. Okay, ux prime is 0.85 c, v is minus 0.65 c. Plug in those numbers, and I've simply left out this, because this has a c with it, this has another c, and then below you have c squared, so they will get cancelled, right? I've not written that. So when you calculate, you're going to get 0.45 c. Just for comparison's sake, in the Galilean addition of velocities, ux would have been just 0.20 c, because it will be like 0.85 c minus 0.65 c. So if you did not consider relativity, you're going to get a completely wrong answer, which is 0.20 c. And this question A negative muon traveling at 43% of the speed of light collides head-on with a positive muon traveling at 55% of the speed of light. The two, each of mass 105.7 mega electron volt by c squared, annihilate and produce how much electromagnetic energy? This is a case of mass getting converted into energy. So you have the two particles and their velocities, and the total energy is going to be the energy of the first plus the energy of the second, right? And the energy of each one is gamma mc squared. And since they are moving at different speeds, it's gamma 1 mc squared plus gamma 2 mc squared. Surely mc squared can be taken common, and then gamma 1 is 1 by root 1 minus v squared by c squared. The c squared will get cancelled. I'm not writing that. Okay. And now remember that the rest mass of the muon is 105.7. Rather, the rest mass energy is 105.7. Just like the rest mass energy of the proton was 938.3, right? So this would be given to you. That's a constant, which is the rest mass energy of the muon. When you do that, calculate, you get 243.6 mega electron volts is the total energy that's going to be released. In a nuclear reaction, two identical particles are created traveling in opposite directions. If the speed of each particle is excuse me, 0.85 c relative to the lab frame of reference, what is one particle's speed relative to the other particle? Interesting. The speed of each particle is 0.85 c for a person who is in the lab and watching these two move in opposite directions. The question is, what is the velocity of one relative to the other? Again, we got to use the relativistic addition of velocities. One is moving negative, the other is moving positive because they're moving in opposite directions. Yes. And the one that's moving to the left or to the negative side is the S frame. The lab is the S prime frame. Remember in the last question, the Earth was the S prime frame, right? So always the S prime, just take that as the one that's not moving, like the Earth or the lab. So the velocity of the lab relative to the negative one, so velocity of S prime relative to S would be called V, and that is 0.85 c. Okay, and now the velocity of the one that's moving in the positive direction relative to the lab, that is what is called Ux prime, would be 0.85 c. So use the formula. Ux is Ux prime plus V divided by 1 plus V Ux prime by c squared, right? Plug everything in carefully and calculate. Both those are 0.85 c. And this time I'm writing everything down. Just notice that the c's, the two c's here and c squared will get cancelled. When you calculate this, you get it as 0.987 c. This is a very important chapter and important problems that you really have to take time to understand. So good luck with that.